In this lecture, we're going to look at convolutional networks and how we can implement them in TensorFlow using the Keras sequential API. So these convolutional layers, are more complex than the simple dense layers that we've been looking at so far. So we tried implementing multi-layer perceptrons in TensorFlow using basic operations, but now that we start doing some more complex architectures, we're going to start using Keras to make it easier to create these networks. I'm going to start by explaining what is this convolution operation and explain convolutional layers that are used in the convolutional neural networks. Both the convolutions and pooling, which is also often used, and I'll be using as an example image processing. This is not the only case where we can apply convolution layers, but it's a very common application of convolution networks for image segmentation, image classification, and so on. And so I'm also going to give a brief introduction to the sequential API on Keras and talk a bit about the tutorial for today, where we're going to use classification with convolutional neural networks on the fashion-NIST dataset. So let's start with the convolution operation. Mathematically, a convolution of two functions given some displacement time t, or a displacement value, this could be an abstract coordinate, but usually we can think of it as time, is the integral of the product of the two functions, one of them displaced by t, and with the input values switched, so we use the negative of the input. So like we are inverting the direction of the input for that function. This can be done, this is commutative, so it's the same if we multiply f of tau times gt minus tau for all tau, integrate for all the tau, or if we do it the other way around, changing f and g in places. Now, this is very hard to understand in abstract what this can be useful for, but one intuitive application that is easy to understand, it's in linear time invariant systems. So a linear time invariant system is a system that responds linear to some perturbation. For example, suppose that we have a bar of iron and we can hit it with a hammer, and this would be the oscillation of the iron bar. When we hit it with the hammer, it starts oscillating and then it dampens and it stops again. So if this response is linear with the strength of the hammer strike we are giving it, so with twice the strength it will have twice the amplitude, this will be a linear response. And time invariant, it means that it doesn't matter when we strike it with the hammer, the shape of the oscillations will always be the same. So it doesn't matter if it's at time 0 or if it's at time 1 or something like that, it will always vibrate in the same way. Okay, so imagine that we want to figure out how the bar will move if we give it 2 taps with the hammer in a very quick succession. So 0.2 seconds in interval, we strike and strike again with the hammer. In that case, what would be the oscillation of the iron bar that we're hitting? We can use convolution to compute that by taking the symmetric of the response function. So this is the same as what we had here, but we are inverting on the time axis. And now we compute the convolution between the symmetric of the response function and the function describing the two hammer strikes that we are hitting the bar with. So at time 0, nothing is happening because we are multiplying by those zeros. When we reach the time where the first hammer strikes, we start having this oscillation, and then the second strike, and this is the function, the convolution function as a function of t for different time displacements by computing those integrals, those operations on these two original functions. So this is one possible application of convolutions, by seeing what is the response of this linear time invariant system to a particular impulse, but we can also think of this in a different frame by inverting the problem. And now suppose that we have some signal over time. This is always the intensity of the signal, for example, as time goes by, and we see that it's changing with these curves, but then there is this pattern here that we want to detect. So we can create a function, a detector function, that simulates, that is the same as the pattern, but in this case inverted in the x-axis. We are computing the symmetric of this function, and now we can compute the convolution of the two with different time displacements. And if we are considering time displacements that do not match the pattern, we have a very small result here. When they start matching parts of the pattern, we have these peaks, but when there is a superposition between our detector and the pattern, we have a very large peak here. So basically, using convolution operations, we can detect specific patterns in an input vector when we assume that the input is giving us always the same thing, but for example spread out over time or spread out over space or something like that, where it makes sense that we consider this shift and compute these products of the detector function and the input values. So this is basically the idea behind using convolution networks to deal especially with unstructured data. Note that it doesn't make sense to do this if we have a table with different features on the columns. It doesn't make sense to slide this detector over the different columns, because the columns are signifying different things in the case of structured data. But if we have something like an image or a time series or something like that, then it makes sense to slide along the input and try to find these patterns. So if we are dealing with a continuous function, this is the formula for convolution. We can have the equivalent on discrete functions. So in this case, we are just summing the products over the different values, but taking the symmetric of one of the functions and using some specific displacement. And we can consider this particular function that we are using to be some sort of detector to try to find the parameters. And we can imagine that if it's a function like this, we don't really need to specify all the values here, because all of these are 0. We just need to specify a set of values here. So if we are dealing with a discrete function with a finite time window, we just need basically a vector or in general some sort of array of values that we're going to use in these multiplications. So this is the kernel here. The kernel is this array of values that we're going to use to multiply the input with different displacements and add up to compute this convolution function for each displacement. So in practice, for convolutional neural networks, this kernel will be a finite set of values. So in general, a tensor. It can be one-dimensional if we are dealing with one-dimensional data, two-dimensional if data is two-dimensional, and so on. And so this is a finite set of parameters that we can think of as the weights of a neuron. We are going to multiply these by the function, and we're going to compute the result of this product. If they are vectors, we are computing the inner product there, or in general, we have this kind of expression where we are adding all of the products of our kernel with the corresponding inputs over all the possible space. But in this case, we are considering only the window corresponding to the kernel, because everywhere else it's 0. We can do this with vector multiplication, with matrix multiplication, and so on. But you see, this expression looks like what we're doing with neurons when we process the input over the weights of the neurons. So let's see how we can use this in a neural network. One simplification that we can do is, instead of indexing on the kernel that we have here, we can imagine that we are indexing on the input. So basically our kernel is fixed. but it's sliding over the input. This is the idea of this animation that I did here. So we have this kernel for detecting the pattern. The kernel is sliding over the input. We have this map of the activations over different time displacements. So this is called the feature map, and we can see a peak there where our kernel detected the correct input. So this would be the idea on neural networks. We have the kernel sliding with some displacement over the input. The input can have more than one dimension. So in this case, it can be a two-dimensional input, and we can slide the kernel over this matrix. Another difference is that there is this inversion here when we see in the convolution function that we have, for instance, in this case, we are computing the integral as a function of tau, but as a function of minus tau on the other function. This is necessary for convolution to be commutative, but we don't really care about that in convolutional neural networks. And the only difference here would be the symmetry of the kernel, so it doesn't really matter. And what we actually do in convolutional neural networks, even though it's called convolution, it's actually a cross correlation, because we don't do that kind of inversion that only complicates the computations. We just slide the kernel over the input, multiply each weight of the kernel by the corresponding weights on the input at that particular window, and add everything together to get the result. We call it a convolution, even though strictly speaking it's a cross correlation, but the name itself is not very important. The important thing here is that in a convolutional neural network, these weights of the kernel will be learned by the network, so that the feature map that results when we slide the kernel over all the input will identify useful features for minimizing the loss function, so for solving the problem that we want to solve, like classifying images and so on. So let's see how a convolutional neural network works. We can think of it as deriving from the standard multi-layer perceptron, from the dense networks, but by using only sparse connections, sharing the parameters, and this in turn gives us this property of equivariance. So I'm going to explain each of these a bit better. The idea of having sparse interactions is that when you have dense layers, like in a multi-layer perceptron, the neuron in one layer is connected to everything in the previous layer. This can be the inputs, or it can be a previous hidden layer, it doesn't matter, but we have lots of connections here between everything in the previous layer and each neuron in the next layer. In a convolutional network, we have just a kernel that has a finite size. So it's something like we saw here. We just need this part here to define our detector kernel. So in this case, the connections are sparse because each kernel is only looking at a small field. Each neuron here is only looking at a small field on the input. This saves a lot of parameters in the weights. But note that the receptive field, which is the region on the input from which each neuron will receive information, each kernel will receive information, can be quite large when we stack these networks. So even though this neuron here is only getting data from these three, so it has only 3 inputs on this layer, the receptive field on the data itself is larger, has these 5 inputs, because these in turn will be dependent on the whole set of 5 inputs here. So the receptive field in the input layer can be large for kernels that are deeper in the network, even if each kernel has only a small window, as long as we have enough layers between them. Another property of this kind of layer is that we are sharing parameters. When we have a multi-layer perceptron or a dense set of layers, then the parameter that goes from this input to this neuron is different from all the other parameters. But if we imagine that we have a kernel here that we are sliding over the input to produce all these outputs, then this connection here, the weight that is connecting this input to this output, is the same as the one connecting this one to this one and this one to this one, because we are sliding the same kernel over the inputs. So this means that we have far fewer parameters to optimize when we are using convolution networks than if we were using dense networks that would supply the same number of outputs. So here's an example of what we can obtain with a convolutional network. In this case, suppose that we create a very simple kernel that has a -1 and a 1 as two weights. So basically, for each pixel, we are taking one pixel and subtracting the pixel on the left. And this would be the feature map here. If we are changing from white to black, so black is here on the right, white is on the left, white is larger, and if we are subtracting it from black, we get a very low number here. When things are smooth, we get this gray, this intermediate value, but when we change from black to white, then we have a large value, and this is a lighter color here, and so on. So by sliding this kernel over all the image in both dimensions, so we are sliding over all these metrics, we get a feature map that is detecting these variations in color from one pixel to the next. And this would be a simple detector of this kind of attributes in the image. Note that when we slide the kernel over all the input, we get a feature map that has, in this case, it can have as many outputs as the input. We'll see this a bit in more detail, but we are always using the same kernel. It's always this one that is sliding everywhere. So we don't have a huge number of parameters to adjust. We just apply the same parameters over all the input space. So the property of equivariance comes from this consequence of the way we're computing this, in that if we translate the image, if we shift the image to one side, we get exactly the same shift on the output. So you can imagine that if the dog is shifted to one side, we get a shifted dog here on the output. If we shift the dog down, we get this feature map shifted down. Not all operations will be equivariant. For example, if we rotate the dog or mirror the dog, then we change the order of black to white and white to black, and this will actually change the feature map in different ways. But there are some transformations that, if they are operated in the input data, they will result in the same shift in the feature map that is output by the kernel. So these are good properties for dealing with unstructured data, because in this case we may want to find some specific patterns without having to specify where the patterns appear. We may be interested in finding the dog eyes and the mouth and things like that, but in dog pictures this could be in different positions in the image, so we may need to have these detectors that can look everywhere, and we don't have specific columns with specific features like we have in structured data. So convolutional networks are very useful for dealing with unstructured data. They can be images, it can be some time series, for example, or some sound waves or something like that in one dimension. It can even be in 3 dimensions, for example, looking at different shapes of proteins, molecules, things like that. So this is how the convolution layer will work in practice. We have an input. In this case, I'm assuming that is a 2-dimensional input. This would be the example of a grayscale image. If we have a color image, this will have actually 3 channels, because we have red, green, and blue, but the idea is the same. And for one convolutional layer, we can have some number of neurons or some number of kernels. Each kernel will consist of a set of weights that will be multiplied by this receptive field here. The name of receptive field comes from biology, from the physiology of the eye, of the anatomy of the eye and the nervous system, because that is what is called the region in the retina from which neurons in the visual cortex, so in the back of our brain, receive input when they are processing visual data. So the receptive field is the set of neurons in the retina that will feed each neuron in the visual cortex. And the idea here is that each neuron in the convolutional layer will map to some receptive field in the input, where it will be sliding and computing all these different values in the feature map. So the way we can imagine this working is that this neuron here has a set of weights. The weights are marked here in red, and we are sliding the neuron on the input. And for each position, we are multiplying the weights by all the inputs and adding everything together into a feature map. So this neuron will generate a feature map here that is a function of the inputs and the weights. This second neuron will generate a second feature map, and the third feature map, and so on. So the convolution layer has n neurons, or also called filters, and will produce these n feature maps by applying the kernel to the whole input. So we can represent the output of the convolutional layer in this way, where we have the different values here in width and height depending on the input, and the depth that depends on the number of neurons we have on the convolutional layer, because this will generate a number of feature maps. And typically when we are creating networks for image classification, for example, we generally keep shrinking the size of the feature maps but increasing the depth. So detecting more and more features but reducing the spatial resolution so that we do not worry too much about where in the image each feature is appearing. And then, since convolution is a linear transformation and we need to stack these convolutional layers with non-linear transformations, otherwise it would not be helpful, then all the feature maps are also passed through an activation function, typically the rectified linear unit. So actually the feature maps are the result of using the kernel to multiply the weights by the inputs, adding everything together, and then passing through the activation function to produce this map. The feature map then will be fed into another convolution layer, and so on in a deep network. So some details about the convolution operation. The depth of the stack of feature maps that we will obtain is given by the number of filters that we are using. That is the number of kernels or the number of neurons that we have in that convolution layer. The stride is the step by which we are shifting the receptive field when building the feature map. For example, here we have a stride of 1, which means that at each step we are just moving one location in the input matrix. And this will produce these values like this. If we use a stride of 2, in this case, we are skipping some locations, so we are giving steps of size 2, and we will produce a smaller feature map. So by using strides, we can also reduce the size of the feature map in this way. We can also use padding to prevent the output from shrinking. So here is an example where we do not use padding. So we have an input of 5 by 5, but the output, the feature map, is only 3 by 3. The reason for this is that we only have 3 valid locations along each axis that do not put some weights of the kernel outside the input matrix. And so by not using padding, we reduce the size of the feature map with respect to the size of the input. If we don't want that to happen, we can add padding, for example, zeros all around the input. This can be done virtually, but we can think of it in that way, so that we can access all the coordinates of the input with our kernel, and so produce a feature map that has exactly the same number of locations, the same dimension as the original input values. So this is one thing that you can do. You can use padding to prevent the feature map from being smaller than the input. Here is an example of a network for classification, a convolution network. You have convolution filters here. So each of these will be the output of multiplying all the regions of the input of this image by some kernel. And the kernels are looking at different aspects of the image, different patterns. Then we apply the rectified linear unit for a nonlinear activation here. And then we do this again a convolution by looking at the output of these filters. Now, one thing here in order to understand this is that if you have a single channel as the input, then the weights of the neurons will be just for this input in 2 dimensions like we see here. But you can have several channels on the input. For example, a color image could have red, green, and blue. So this means, in that case, if you have 3 channels, each of these kernels will have 3 times more weights, because they will also have weights for the second channel and the third channel, and is adding, multiplying and adding everything in that volume of all the channels in the receptive field. So this is what happens when you have another convolution layer. And in this case, the convolution layer here, each of these kernels is going to scan through all of these feature maps at the same time and look and aggregate the patterns over all of these feature maps. So this is one kernel that looks at all this information and produces this feature map. This one also looks at all the information, so all the results of the rectified linear unit here, and produces this one that, after passing through a rectified linear unit, produce all these patterns. Another thing that we can do is then, after doing convolution, we can use pooling to shrink the size of the feature maps. So this is done typically between convolutions, because we may want to aggregate the outputs of several pixels, several locations on the feature map, in order to reduce the size of the feature map and make it less sensitive to small changes in position on the input. So the idea of pooling is to use some aggregation function that can reduce the size of the map that we're using. For example, with max pooling, we take a region, we take the maximum value, and that is the one that we keep. Then for other region, the maximum value, and so on. And we shrink from a 4x4 map into a 2x2 map in this case, because we are using a window of 2x2 and a stride of 2. Of course, we can change this, we can change the stride, the size of the window, but typically we are going to use a stride of the same size as the window, so that there are no overlaps between the different regions, and we cover the whole input feature map. There are different aggregating functions that we can use, averaging the root of the mean of the squares, things like that. But max pooling is perhaps one of the most widely used, since it's very easy to compute, and it makes the model more invariant to small shifts, because if you shift this 6 over to this side, for example, or up or something like that, then it will probably still be a 6 on the output here. So this is, in this example, we are using convolutions and then pooling, and then more convolutions, pooling, and so on, and we are shrinking the size of the feature map until we reach here the end, and we pass over to fully connected layers for classification. So this is the general idea when we are using convolutional neural networks for classification. We have these convolution layers that have, in this case, they have many filters. For example, here 48, 128, 192. They have these pooling operations that shrink the size of the feature map as we increase the depth. So we are converting information that is spread out geometrically over the image into features that we are identifying and storing in these different filters. And then we are going to pass everything to dense layers where we do the classification here. So in this case, there are 1,000 different classes, and classification is done here at the end with softmax. This is the AlexNet, was one of the the first networks of this sort to be used in these competitions for in the ImageNet dataset for classifying images. Another use of convolution networks is, instead of passing on to fully connected layers, we keep doing convolutions, but now we do upsampling, and we convert back from a large set of features that were shrunk, where the feature map was shrinking into a large set of features, but a small size of the feature map, and then we go back and recreate a map from there. And this can be used for image segmentation. For example, in this case, semantic segmentation, we have one color representing the sofa, another representing the cat, another representing the dog. So the neural network is identifying which pixels correspond to which entities in the image. And this can be done with a fully convolutional network, where the output is also a feature map indicating these different categories. Okay, so I'm not going to detail much about the fully convolutional networks. We're not going to do image segmentation here, but this is just to give you an idea of the difference between classification and segmentation. But we're going to use convolutional networks for classification. These layers are harder to implement, so we're not going to waste time trying to implement them with basic TensorFlow. We're going to use the Keras interface, because it has all of these classes that already implement the different layers. So we'll start by importing, for example, the one optimizer, like stochastic gradient descent. We import the sequential model. This is the one we're going to use. This is a good class for when you just want to add layers in sequence and don't want to build more complex architectures. We're going to see next week the functional model when we want to do we need more flexibility to do other tricks, but for this first approach, the sequential model is easier to use, and it's enough. And now we can import the different layers: batch normalization, dropout, the dense layers, the convolution layers into dimensions for the images, the activation layers where we specify the activation, and so on. So to build a network with the sequential model, you create an object of the sequential class, and then you use the add method to add layers to the network. For example, we want to add a two-dimensional convolutional layer with 32 filters, a kernel that is 3 by 3 on the input. We use padding. Padding same means that the input is padded with zeros, so that the feature map retains the same size as the input. And in the first layer, we need to specify the shape of the input. We're going to use this with the fashion NIST dataset. This is similar to the NIST dataset that you saw last week. It's also images of 28 by 28, but this one is a bit harder to classify than just the digits. These are 10 different categories of clothing. They have the cartoons for the different types of clothes. But other than that, it has the same shape and the same type of matrices that we have in NIST. Also 10 classes, the same size, 28 by 28, grayscale. So here we specify the size of the input, which are going to be images of 28 by 28 with only one channel. By default, in Keras, the channel is the last dimension. Note here that the actual input to the layer will have one additional dimension because we are feeding batches into the network. But when we specify the shape of the input, we are specifying only a single example. And a single image is a three-dimensional matrix that has 28 by 28 and one channel in depth. This is what the convolution layer is expecting. So this is the parameters for the convolution layer, and we are going to create an object of this class and add it to our model. And then we can add an activation. You can specify the activation also here, but I'm separating the two in this case. Conceptually, I think it's a bit clearer. and we're going to add a rectified linear unit activation, and we're going to keep doing this, for example, adding max pooling. So in this case, max pooling, we use a size of 2 by 2. By default, the stride will be the same as the size in each dimension, so we don't need to specify that. And then we have more convolutions, and now we want to do this step here, where we pass from the convolution layers into dense layers. The feature map that outputs from convolution layers will be a three-dimensional matrix for each example that will have a width and a height depending on the pooling that we did, and the depth that corresponds to the number of filters. For example, for this convolution, the depth is 64. If we already shrunk this from 28 to 14, then the output would be 14 by 14 by 64 for each example. If we have a batch of 32 examples, then we would have an additional dimension with 32. But in any case, we need to convert this into a matrix where all these 14 by 14 by 64 features are in columns in our matrix, so that we can feed it into the fully connected layers that are called dense here. And for that, we're going to use flatten. So flatten is a special layer in Keras that will flatten everything except the first dimension, because the first dimension is the dimension where we keep the different examples in our mini batch. We don't want to flatten that one. And basically, you're going to use flatten when you step from convolutions to dense parts of your network, because you need to adjust the input, not be a multidimensional feature map, but be one vector for each example into the dense layers. And now we also add the activation, and here we can include batch normalization, dropout, and so forth to help with regularization. So just a quick note here. If you search the internet, you can find many different opinions about this, but the one that seems to be consensual and makes more sense is that you use batch normalization after the activation, so that the input to the next layer is standardized. And this is important because if you do it before activation, then what inputs the next layer will not be standardized. And you should use dropout only after the batch normalizations. The reason for this is that after training, so during training, the batch normalization is keeping the running averages of the activations. And the dropout is disconnecting or turning off some neurons at random. After training, the batch normalization statistics that were collected during training are fixed, and now all those values, those rescaling parameters, will be used exactly the same for all the examples that we want to predict. However, the weights are now rescaled on any layer that was affected by dropout. The weights are rescaled to change, to calibrate the average output of those neurons. So the combination of these two things, by keeping the same statistics and rescaling the weights, can give you some harmful effects on the performance of the network if you use dropout before batch normalization. So generally, use dropout after batch normalization to prevent these problems. And also, even though dropout may have some benefits in convolution layers, in general it doesn't work very well, and it's significantly different from dropout in dense layers. So as you saw, the effect of dropout in dense layers is to implicitly train a large number of different networks generated by the combinations of neurons that are turned on. But if you use dropout in a convolution layer, you are turning off parts of the feature map. So this is not really using a combination of networks, it's just hiding parts of your input at random. And this may be helpful in some cases, but it works differently from the original intention of dropout, and may not help very much at all when you use them in convolution layers. So don't just spread dropout layers everywhere. Think about where they may be more helpful. And then after we define the model in this way, so we add all the layers to our sequential model, we create an optimizer. In this case, I'm including momentum and also something that I didn't speak before, but you can include a parameter here for decaying the learning rate. This means that the learning rate will be multiplied by 1 minus whatever value you put here at each epoch, and so it will slowly shrink. So you can put a small value here, for example, the initial learning rate divided by the total number of epochs that we want, and at each epoch the learning rate will shrink slightly. This makes it easier to take advantage of the benefits of a large learning rate in the beginning, where we want to quickly approximate some reasonable result, and without having the disadvantage of a large learning rate at the end of training, where it can prevent us from converging to a good solution. So this way, the learning rate can start higher and then start shrinking during training. Now we create the model. So this is basically the function to create the model. I just implemented it outside. But after adding all these different layers, we compile the model. When you compile the model, you specify the loss function that you want to have. So in this case, it's categorical cross entropy. We are using the softmax output here in a dense layer that has as many neurons as the classes that we have in our problem. And we include the categorical cross entropy in this case. We specify the optimizer, and also we may want to add additional metrics. When you train these models, they will Keras will output the value of the loss function, but you can add additional metrics if you want, for example, accuracy, so that you can also see that during training. Note that when we implemented this in TensorFlow using the basic operations, we had to take care not to include this softmax activation when computing the categorical cross entropy because of numerical stability and so on. But Keras does that automatically. So when we compile the model specifying this loss function and this output in the last layer, Keras understands that it needs to create those other alternatives with the logits and the cross entropy from categorical cross entropy from the logits and so on to avoid numerical instability. So all of those things that take some work implementing, Keras is hiding them, and that is one of the reasons why we start with basic TensorFlow, so that you can understand these problems before sweeping them all under the rug with Keras. Okay, so now to train our model, we just need to call the fit method. We specify the training set, the features, these are the images and the labels. We can include validation data. In this case, I'm using the test set. This is not very correct if you want an unbiased estimate of the error at the end. You cannot use the test set for monitoring training or for early stop or things like that. But since in this case I'm not particularly concerned about that, I'm using the test set just because it's convenient. In more serious problems, you should split the training set into training and validation and retain the test set at the end. This is the batch size, the number of epochs. You can specify these constants as you wish. And then at the end, we can save the weights for our models. This is convenient because we can then recover our model by creating the model again and loading the weights. As long as the model is exactly the same, you create exactly the same model, things will work because Keras will put the weights in all the correct layers. And you can then load your model and use it. You can also save the complete model, but I prefer to save and load the weights and generate the model programmatically, because if you save the whole model, sometimes there are issues with different versions of TensorFlow, and saving the weights is more robust to those kinds of problems of different versions not being compatible. You can also call this summary after compiling to see a description of your model, and you can add callbacks for including data into TensorBoard. So Keras has this TensorBoard callback where you specify the folder where you keep your logs, whether or not you want to write the computation graph, and then you just add this as an additional argument in the fit by specifying the different callbacks. And these are functions are executed during training, and in the case of the TensorBoard callback, it will store your metrics and the loss values and so on, so you can follow it in TensorBoard if you want. So basically, Keras simplifies a lot of those things that we've been doing and allows you to create more complex networks without worrying too much about the details of the implementation. The fit method also returns a history object that has the values of the metrics that you selected. So both the loss and this is the training loss, this is the validation loss if you include validation data, and also the metric that you chose. We chose accuracy when we compiled the model, so we have the accuracy on the validation set and on the training set, and so you can keep this object if you want to plot these things yourself. Okay, so for the tutorial, you're going to use this data, the fashion NIST. This is the GitHub page where you have the data set, but you don't need to use that page. You can load it from the Keras datasets module. So this works the same as NIST. When you use load data on fashion NIST, it will check if you already have it on your drive in cache. If you don't, it will download it, and then you can access the data. So we have the training and the test set separated, exactly like in the NIST, 60,000, 10,000. And then you do the same thing. You reshape and you convert into float 32 between 0 and 1. This is useful because if you start with values that are too high, you may have some problems with convergence. The difference between this exercise and the one we did last week is that last week we were using multi-layer perceptron, so we converted the images into a single two-dimensional table where each row was one of the images and each column was a pixel in the image. So we had 700 and something pixels on the columns. In this case, we are using convolutional networks, so we are trying to scan through the image, keeping the spatial relations between the pixels as they were in the image. And since our convolutional layer is expecting to have examples of this shape, so 28 pixels by 28 with one channel, this is only a grayscale image. If this was a color image, you would have 3 channels there. So that's how we're going to reshape. We're going to reshape our training images to have the same number of rows, the same number of examples, but then 28 by 28 by 1. So we have all of these images like this, the same for the test images, and we're going to create these one-hot encodings for the labels. This is the same thing that you did last week. Remember that we have labels 0, 1, 2, and so on, and we need to convert that into that representation where we have a vector of zeros with a 1 on the correct class, so that we can compare with the softmax output of our network. Okay, so the model that I propose you use for this exercise will have a first stack of 2 convolutional layers and a max pooling, where each convolutional layer has a 3 by 3 kernel. Use the same padding so that you don't shrink the output during the convolution, and 32 filters with a rectified linear unit activation, and you can use batch normalization here. So this is similar to this kind of network that we saw here. You see where you have 2 convolutional layers and then you have pooling. We're going to do the same thing. So I recommend you start with this model where you use 2 convolutional layers in this way, and then you do max pooling of size 2 by 2 with the same stride. So by default, the stride will be the same. And optionally, you can experiment adding a dropout layer after pooling. But remember that dropout is not generally very good with the convolution layers. So just experiment that, but don't expect any improvement. Probably you get some degradation on the results. The second stack is the same as the first, so all of these elements, but you're going to use 64 filters instead of 32. So we shrunk the size of the feature maps, but now we are adding depth using more filters, more neurons here. And then you need to pass to a dense layer of 512 neurons with rectified linear unit activation. Remember that this transition here, you need to flatten the tensors so that you can fit them in the dense layer. Here you can use dropout, for example, of 50%, and then you can add the softmax layer and use this optimizer. You can experiment changing the network. You can simplify the network, reduce the number of filters, take convolutional layers, add convolutional layers, add more layers to the dense part, do some changes like that. And when you do this, do also this part, the summary of your model, so you can see the differences in your model as you change the architecture. So this is a good exercise for you to get some feeling on what things are doing, because it may seem counterintuitive, but often in these types of networks, nearly all of the parameters will be here at the end on the dense layers. The convolutional layers have much fewer parameters than dense layers. And as you add convolutional layers, you actually reduce the number of parameters in your network if you also add pooling layers to reduce the size of the feature map and so on. So you can experiment with this a bit and see what effects these things have, and that would be the main exercise for today. Okay, so to sum up, we saw what convolutions are, how we can use them in convolutional neural networks. This is not a good approach for structured data because it makes no sense to slide over the columns of a table where each column is a different type of attribute, but it's very good for unstructured data when you are looking for patterns in the input. In time series, in images, in sound files, and things like that, you need to slide your detectors over the input to find the appropriate patterns, and these will produce the feature maps indicating where those patterns were found. We also talked a bit about fully convolutional networks, just so you have an idea that convolution networks are not just to finish in some dense layer and then do classification. You can use them for other things. We started looking at the sequential API on Keras. So the exercises for today will be first re-implementing the miles per gallon problem with a simple multi-layer perceptron, but using Keras just to see that mechanic of compiling the model, fitting, and so on. So you see how easy it is to do it, and then solve the fashionist problem with the convolutional neural network. In the next week, we're going to talk about the functional API. So the sequential API in Keras, that sequential model, is very simple to use, but only allows you to stack layers in your network. If you need more complex operations or different architectures, then the functional API is more flexible. It's a bit more complex, but it gives you more flexibility. We're going to see that next week. For the assignment, for the first assignment, you need to know both you need to know the basic TensorFlow approach, the sequential, and the functional API. So you still don't have all the subject matter you need for the assignment, but I've put some indications on the first assignment on the website, and you can start thinking about how you're going to do that. Basically, the assignment is for you to write a tutorial showing how to implement these networks with the basic TensorFlow and these two models in Keras, the sequential and the functional APIs. You can start thinking about the examples that you're going to use and the kind of things that you're going to do even before you have all the information that you need. So for this part, I recommend that you read chapter 9 of the book and also take a look at the Keras guide, where you'll find the documentation for the API. This is not something to read in one go, but it's a good idea to know where it is and how it's structured, because every time you're using these layers, it's good to check if you're using the right parameters and so on, especially in the beginning, by looking at the documentation. Okay, so I'm going to log into Zoom and we can talk a bit before the tutorial. See you soon.